Hello everyone, can you hear me? Good. Can you see my screen? Perfect. Okay. So give me a second. I need to show you something. Okay, so I don't know if you noticed already, but I uploaded two extra videos, right? So they're already on the web page. Give me a second. Yeah. So yeah, one is for the midterm questions and the other one is for these multiple joins, basically the transformation bonus, right? And remember, this is, I mean, for the one of the bonus, maybe, I mean, not everyone was literally trying to get the bonus for transformation assignment, but the topics that I discussed that I'm discussing on that video, we can make a couple of questions in either the second midterm or the final exam, right? So everybody should see those videos, okay? So today we have the PDF already there. I think I probably need to modify. Yeah, I think I need to modify this thing. So yeah, don't pay much attention to the reading suggestions because I think this is wrong. So yeah, so today we will keep talking about ray tracing. Basically, it's like the second part of ray tracing. We will keep talking about intersections and other stuff, right? Good. So another super important thing is that I will not say names, but some people is missing the face-to-face grading. So yeah, please, I assume that everybody signed up, but some people is just not showing to the face-to-face grading. So please, you need to if you know the name of your TA, please send an email. They also will post something on Piazza, so you can kind of like rebook your face-to-face. The thing is, if this keeps happening, right? I mean, we will need to maybe penalize, right? If you need to rebook. We understand that, yeah, everybody can have a problem, but yeah, but I think it's too many people right now that is basically missing the face-to-face. Okay, good. So yeah, let me go to the presentation. Okay, can you see the presentation? I guess. All right, good. Also, yeah, I had another announcement. Well, you already know that, right? That the recorded version of the lectures, I'm uploading those on YouTube, right? So there are basically unlisted videos on YouTube. But some people were having problems to access YouTube due to this VPN stuff, right? And somebody said you should list them. Yeah, probably I will, but yeah, I need to ask UBC because sometimes they are kind of picky. I mean, it's everything is my material, but yeah, I need to ask you UBC before listed. Okay, but the thing is, I was also uploading the videos to Canvas for people that is basically not having access to YouTube. The problem is, so we have a problem on Canvas. Canvas is not already accepting new videos. So we are still missing, I think, the last 3 videos. So it is a problem. It is something that is a problem on Canvas. So I'm not sure how many people is having problems with that, but yeah, eventually we will fix it. I hope it will be fixed today. Okay, good. So, and also sorry, but I have a huge headache today, so my brain is kind of blurry. So yeah, maybe today will not be a good day for me. I'm already took a couple of Tylenol pills, but yeah, it's a bad day. Thank you. Okay, good. So learning goals for today. So we will keep talking about ray tracing, like the basic idea of the ray tracing and the very basic ray intersections, which is basically sphere. I mean, we already talked about that, right? The ray sphere intersection, also ray plane and ray triangles, and how we can, with this very simple idea of shooting rays and intersect rays with geometries, how can we create amazing images, right? And also we will talk about depth buffer, which is a topic that is relevant in ray tracing, but is also something that we also do in real-time rendering on the rendering pipeline. So we haven't discussed that yet, but yeah, but we will talk about that today. So again, the ray tracing idea, right, is I have geometry, I have a scene, so I have objects in 3D, I have a camera in 3D, and the camera is obviously represented or is representing an image, right? So the camera has an image plane, which is literally a plane in 3D that it has certain coordinates that they represent the pixels of that camera, right? So imagine that maybe it's an image of 1000 by 1000 pixels, right? So for each pixel coordinate, right, I get a vector, which is basically the position of each pixel minus the position of the camera. I get a vector, and I shoot a ray using that vector through my scene, right, looking for objects to collide, right? So I get, for example, to this sphere in particular, I get the intersection to that sphere. I get information from that object, right? So that is important. Objects in 3D, we know we have information, right? So if it's, for example, in this case, it's a sphere, we have the center of the sphere, we have its radius, we can compute the normal, which is this pink vector, right? We also have other information. We have the color of the material. We have many things, right? So with that information, and also the other information that we have on the scene, in this case the light, we can compute the final color of the pixel, right? In this case, the color of that pixel in particular will be, yeah, kind of a bluish thing, depending on the distance to the camera, the angle to the camera, and all that stuff. So we discussed already that the very basic version of this is ray tracing spheres. So in the 70s and the 80s, where computer scientists were like they were beginning to experiment with ray tracing. Yeah, everything was basically spheres, right? Because a sphere, getting the intersection between a ray and a sphere is very simple. So you will see that everything were spheres in that time, and we already discussed how can we get that intersection, right? So if you forget about these equations, it's obviously it's on the previous session. And by the way, I have another announcement. So if you remember, I asked you to answer a survey. I mean, not everyone has answered the survey, but a couple of people already did, and I'm getting a very nice feedback. And I think in general, people is asking to have more math exercises, right? That maybe I'm covering like the geometrical intuition of these things and showing you formulas, and sometimes I even showing you like coding examples, but we are not having probably like much practice, right? In terms of like several problems of this, for example, here, like 2, 3, 4, 5, or whatever, like simple exercises, having spheres and rays, and for you to practice your math, right? So we will change that. So thank you for your feedback. So we will start to include more examples like that on the tutorials. So I will ask the TAs to basically take the tutorial time to basically solve this kind of math problems. And we will also modify a little bit the way we are doing the quizzes. So the practice quizzes we have at the end of each lecture, they're usually very simple, 4 or 5 questions. Sometimes it's just true or false, or very simple. So we will start to modify those quizzes. We will basically make those quizzes as like more math related with a bit more practice. Okay, so yeah, I hope that could help you to kind of yeah, practice this type of things. Okay, so we already discussed, again, this ray tracing sphere. The thing that we didn't mention the other day is what happens, or how can we know if the ray is actually colliding with the sphere, right? So one of the first things that we compute, or basically the first thing that we compute when we want to compute the intersection between the ray and the sphere, is this distance d, right? So something that I missed the other day is, once you have the distance d, you compare the distance d with the radius of the sphere, right? So if that distance is less than the radius, it means that the ray is actually passing through the sphere, and right, and so you have some intersection. And that voice is my son, very close to my room, talking. So sorry about that. Yeah. So this, again, this distance is basically, if it's less than the radius, it means that the ray is basically colliding with the sphere, right? If it's larger than the radius, right? Okay, then someone is saying, let's see, the sun saw some. My son is he's in fifth grade, so yeah, he's definitely not playing with ray spheres intersection, but he's actually very good. He's very good in math. So if d is obviously larger than the radius, it means that ray basically missed the sphere, right? So the very first part of your algorithm needs to check or compare the distance d with your radius, and if it's larger than that, right, it means that you don't need to compute anything else because there's no intersection, right? So that is something that I missed the other day. Okay, so let's keep talking about, again, the general concept of this, right? So we get a camera, which is the origin of the ray. We have an image plane that it has several pixels, right? So there are a lot of pixels here. And for one of those pixels, I take this vector, which, imagine that, I mean, maybe I drew them up very large, but they are normalized, obviously, right? They are unit vectors. And then we compute everything that we already discussed, and we get to the intersection to the sphere, right? So then we need to compute the color of the sphere, right? So what information do we have? We have the intersection point, we have the normal, which, if you remember, is basically this position minus the center of the sphere. So in case of spheres, getting the normal is very simple. So there are no, we don't need to construct a sphere using triangles or things like that. I mean, it's very simple. So what else do we need to compute? For example, the Blin light color equation, right? So remember, we need the ambient component, the diffuse component, and the specular component, right? So ambient component, it's only the color of the material, and is the component in which we are like faking lighting coming from everywhere, right? So that is only getting the color of the light in that case, right? Then we have the diffuse component. The component needs to also combine the color of the material with the color of the light. I think I'm already discussed this with someone. So this is important. Remember that we have in our formula that we are basically multiplying the color of the material times the color, multiplying by the color of the light. And this is because if I have, for example, an object that is, I don't know, like blue, and you have a light that it has a color red, your object needs to change color, right? Because it is affected by red light. So the final color of your object needs to be kind of purple. So we need to combine those colors. And also, someone already noticed, and it was a very nice observation, the type of things that I want to see in Piazza. Somebody already noticed that when you're doing your shader assignment and you're changing the color of the light, you will notice that if you change the color of the light, for example, to a dark blue or something like that, the light will appear to be dimmer, right? So the intensity of the light will be dimmer. And you might think that it's a bug and that I'm doing something wrong, that this is a problem. But it's not a problem. Actually, that happens in real life. If I have this scene right here, for example, and I take this light, and let's imagine that I have that this light is totally white, and I get like a transparent plastic or a reddish transparent plastic, like cellophane plastic, and I cover my light, right? Basically, the light coming out from this lamp or from this light source will now be red. But that is because this filter or this plastic sheet will be basically filtering all the light except for the red, right? So less light is coming out from the lamp. So yeah, that is something that happens in real life. If you change the color of something by just covering or filtering, the amount of light that is coming out from that lamp it will be less, so the intensity of the light will be dimmer. So that is something that you will notice on your assignment. Don't freak out, that is perfectly normal. What happens is that the intensity of the light is basically the sum of the RGB values, right? So if the light is completely white, right, you have a certain intensity. If you change the color of your light and now it's, I don't know, dark blue, well, yeah, blue is obviously darker than white, right? So the sum of its components, the sum of its RGB, will be obviously less than the sum of components of a white light. So the intensity will be less. Okay. So again, we have the intersection, we have the normal, we have the light vector, right, which is basically light minus this intersection. And what else do we need to define the color of this guy? Nobody's answering. Okay, we need to check if we are not under shadow, right? Because remember, if something is blocking the light, right, it means that I need to, again, modify the color of my object, right? So I will need to throw a ray on the direction of the light, right? So basically in the direction of this L, right? I throw another ray, and if I hit something between me and the light, right, it means that I'm under shadow, right? Remember that? We already discussed about that type of shadows, ray trace shadows, right? You agree? Are you listening to me? Okay, good. Yeah, perfect. Okay, so in this case, nothing is blocking, right? So we're perfectly good. But what happens if my material, for example, can have different properties, right? So I can have a material that is reflective, right? So again, imagine that you take a plastic sphere or something, and you start to polish, right, this material. Well, you get a stone, even a stone, right? And you just start to with using sandpaper, you start to polish that surface. Eventually, the surface will be reflective. So if it's reflective, it means that now you need to compute other stuff. You need to compute a reflection ray. So reflection in ray tracing is very simple to do, it's very simple to implement, because in the end it's exactly the same idea of ray tracing. So you take the information you have, right? You have the ray vector, you have the normal vector, and you compute basically a reflection ray, right, using the normal and the ray. This is something that we already covered, and you have the formulas or when we talk about Phong and Bling, right? That is already there. So now you have, right, this reflection ray, and we shoot another ray, right, into the scene, searching for objects that we basically collide with that ray. So in this case, that ray will collide to this sphere right here, and this sphere has a different color, right? So imagine that this sphere has a material that is 100% reflective. Basically, it's like a chrome sphere, right? Like a mirror, right? So what will be the color of this pixel? Blue or purple? If it's 100% reflective, what do you think? Blue, purple, or kind of like a mix between those? Purple, yes. Yes, because it's 100% reflective, right? So basically, when an object or a material, right, is 100% reflective, it has no color. That is important. It has no color, okay? So for example, a sphere inside in an empty space with white background will be totally transparent. You, I cannot tell you how many times I had the problem of students that are like beginning their ray tracing, exercises, right? I mean, they start to coding and implement everything, and they basically start to experimenting with ray tracing. And usually, when you're doing ray tracing, you have a single sphere, because you will see when you do your assignment, you will see that it's very time consuming in terms of the amount of time you need to wait for to see your renders, right? So a lot of people had this problem that they have a single sphere, so they start to implement everything. They implement ray tracing, and suddenly it says, oh no, it's not working because my screen is totally white or totally black, right? And they just spend hours and hours and hours like wondering why my sphere is not, why I cannot see the sphere. Well, because it turns out that your sphere is completely invisible, right? A perfect reflective object inside a room with whatever color of background, with nothing, right? Nothing else there, will be completely invisible, right? Because it basically takes the color of its environment, right? However, if this material, for example, is 50% reflective, it means that I need to take the color that I got with my bleen and everything, right? I need to take the final color of this material and multiply by 0.5, and adding to the color I can get from this other sphere and multiply by 0.5, and basically combine them, right? So 50% one and 50% the other, right? So depending on this, how much reflection it's assigned to this material. So that is how you do reflection, right? Okay, good. So, but now let's discuss a little bit. So we said we need to compute the reflection rate. We need to, now we get into this intersection here. But now, what is the color of this sphere? What information do I need to compute the color of this sphere? And someone is asking, I do not get the role of light in this. Okay, the role of light, you mean on this intersection or on the second intersection when I do the reflection? What do you mean? On the first intersection, I mean, you need the light to compute, for example, the specular component, right? Using bleen, let's say. Okay, on the first intersection. Okay, the first intersection is this, right? If I need to compute, I see what you mean. Okay, if this object is 100% reflective, it means that it has no color, so it only gets the color of this guy. So in that case, you don't need light information for the first intersection, right? Because this object has no color, and it will only get color from the second object. If that is what you mean, yes, you're right. There's no contribution of the light in the case of this guy. Well, no, sorry, no. It has actually, because remember the light, basically we need the light to compute the specular color. So even if you have a reflective surface, if the light is shining exactly on the same direction, that is like bouncing those rays to your eye, you will see basically this, you will see like your specular area, and that specular area will be completely white. So it doesn't matter if it's totally reflective as a mirror, it can be completely white. So you can actually use lighting, right? The light information. Okay, so the thing is, okay, someone is asking, and sorry, I mean, I'm seeing your names. When I say someone is asking, is because I tend to protect your privacy, because remember, these videos are in the end up there and in YouTube. Okay, so even though the rate from the camera has different color for 100% case, I don't understand your question.
I mean, if the...
Give me a second, because I cannot hear you. Give me a second. Yes.
Can you hear me?
Yeah. Give me a second.
Can you hear me?
Yes,
now?
I can hear you. Yeah.
Yeah. I mean, if for the 100% reflective case,
Yes.
if the ray has color like blue or red, will that affect the final color of the
Okay.
at the point five?
The rays don't have color. The ray doesn't have color. So
Okay.
that's why I don't understand your question, because you're saying like if the ray is blue, I mean, it has a color on my diagram because I needed to draw a color, right? But it's not that the ray has a color, right? So the ray is just a geometrical construct to compute this intersection. So let's imagine that you get into this intersection. You need to compute the color of this guy. If the color, let's assume that the sphere is not reflective, right? So if it's not reflective, you only take its color material, its normal, the light vector, and you compute the color of this guy exactly the same as you're doing it on your shading assignment, right? You can use, let's say, blend, and you compute the color. If this sphere is reflective, let's say 50% reflective, it means that you need to create another ray, which is basically a reflection, right? You need to compute the reflection vector between this vector right here and the normal, so you get this guy here. So you throw that ray in searching for something to hit. Then you hit this guy here, right? So now you have the original color from this material. You can compute now the color of the purple sphere. And if your object is, let's say, 50% reflective, you will get 50% of this color plus 50% of this color, and that will be the final color for this pixel in particular, right?
Thank you.
Good. Okay, and someone is asking, what if the color of the light is not white? Well, very good question. Yeah, that is something that I was telling you about. If you see the equations we have for a simple blend, you will see that for diffuse component and also the specular component, we also add the color of the light, right? So if the light, for example, is blue, or yeah, is blue, for example, these objects will need to have a certain amount of blue tint, right? So they will become bluish, right? So imagine that the materials are originally white. If now I have a blue light, my objects will look blue because we have blue light. So in the end, everything is mixed, right? The color of the material, for example, in this case, again, let's imagine that this is 50% reflective, and let's imagine that the light is green. So we have a blue material at 50%, a purple material at 50%, and you will also have some contribution of green, right? Because you have a green light. So you will have that very weird combination on that pixel in particular. Yeah. So yeah, the color of the light needs to contribute also. Okay, and David has a question. Yeah.
So I'm thinking about, like, when you reflect a ray, does it mean like you are kind of like creating a new light on that spot, right?
When I
And you're
when I create this ray,
yeah, when you're reflecting a ray, you're kind of like creating a new light source on eye, right? Is that correct?
Not really, because the light source is the same. The thing is, it's okay.
But
It's
you
like
can't just
yeah. Give me a second. You're almost correct. The thing is, because you're saying it's like you're creating another light source. No, it's like creating another camera, right?
create another.
Because in the end, the ray comes from the camera, right? So basically, what the ray what is doing is kind of representing your eye, right? So
Yeah.
this is our eye. It's like, okay, what am I seeing in this direction? Once you get here, and because now this material is reflective, right? If you are now computing the reflection ray, it's like saying, okay, where this is this surface, right? Where I need to see, right? So it's like getting another camera here and now shooting a ray. Yeah, so it's conceptually speaking, it's like creating another camera. Once you get into this into this
Wait, but
ray again. Give me a second because I lost in my other monitor. I lost my presentation. Give me a second. Now when you get there, right? You also have information from this intersection, right? So now you have the normal of the purple guy, and now you have
yeah.
the light vector from that intersection to this guy here, right?
But if let's say S1 is completely reflective,
Okay.
then it must be reflecting some light onto S2
Oh,
as well, right? So we
okay,
don't
okay.
have like two light
Yes,
source.
yes. Okay, now I understand your question. Yeah, sorry, I was
Uh-huh.
not understanding your question.
Okay.
Okay, yes. Let's imagine that is a very sophisticated. That is something that I will talk about in following lectures. But yeah,
Oh, okay.
the thing is, this is not a super realistic. This is not a physics simulation of lighting. Ray
Oh,
tracing
okay.
is it has a very or you can have a very decent result. You can create very realistic images, but it's
Yeah.
definitely not um, mimicking the reality entirely. Because what happens in reality is that rays or right like the light beams are not coming from the camera. Right? The rays are not coming from the camera. In what happens in real light is that we see something because light come from the light source, right, and
Yeah.
bounce in objects that then bounce to the camera. So what we do in ray tracing is like going backwards. It's like, okay, no, now I will shoot something from the camera and then I will like look for the light. So what you're saying is totally correct in terms of physics. So yeah,
Oh,
that's
that's
totally correct. The light, if you imagine the light as a real light source that is emitting
yeah.
photons, you sorry, my mouse. You will emit this light will emit photons, right? That you can see them as a ray, right? Because they're basically going in straight line. It will emit light, and if this guy is reflective, that light needs to bounce and then touch this guy here,
Yeah.
right? We agree on
Yes.
that. That is
Yes.
something that it doesn't happen in ray tracing. That is
Oh,
that
does
is
that happen?
that it doesn't happen. That is one of the things that we don't have in ray tracing. So for example,
Okay.
imagine that I have, so I don't know, if this is a table, right, and
Mm-hmm.
this is the sun, whatever. I mean,
Yeah.
there's a window
Yeah.
and this is the sun, and you have a mirror here, right, and I'm here, right. You
Mm-hmm.
can move your mirror in order to reflect the light of the sun, right, and
Yeah.
basically
Yeah.
like blind my eyes, right? Right? Like tricking. Maybe you did that sometime with your friends or whatever, right? It's something that you can do. You can basically do that. That effect you cannot achieve. You cannot get that effect with ray tracing. With pure ray
Okay.
tracing, is not possible because the way we are computing the light is basically like shooting rays from the camera into objects, right? So we don't
There's no
know.
light bouncing.
Exactly. I mean, in reality, yes, you're right. Light bounces, right? So what also happens is, um, let's assume for a moment. I mean, your question is very interesting, and again, these are effects that they are not easy to achieve with ray tracing. So let's assume for now, guys, that imagine that S2 is totally white, okay? And imagine that this guy here is red. It's not necessarily reflective. It's just a very a red sphere, but it's like very red. Okay, it's super shiny object red, and this one is white. If someone could see this part of the surface of S2, we'll see that it will be a bit reddish, right? Because basically what happens is that the light that is coming from the sun, for example, will basically bounce in this red object, and then it will tint of red to this object right here. So for example, if in your house you have a white wall, right, and you get a very colorful object close to the wall, and you have a lot of light, the light will bounce in the colorful object, and it will basically um, uh, like transfer a little bit of those colors to your wall, right? That effect it's called color bleeding. So color bleeding is actually, let me show you a very quick, and again, I mean, I will talk about that later, but I can show you very quick, because yeah, that your question is very relevant. And someone is saying maybe though the white object absorbs all the red reflected light. Can is saying sorry, yeah, it's saying sounds like a bonus. Yes, you can also do that as a bonus, but that is extremely difficult. Color bleeding is something that is really difficult. It's not easy. Yeah, you could do that as a bonus for your ray tracing assignment, but it's definitely not easy. Give me a second. Looking for an image that I have here. Okay, is the reflection ray just perpendicular to the ray from the camera? No, I think in this image in particular, yeah, it seems that it's perpendicular. It's just, yeah, it was just a happy accident, as Bob Ross says. No, it's not perpendicular. It needs to, this angle needs to be exactly the same as this angle. It's just, yeah, it was an accident. It looks perpendicular, but it's not, and it doesn't need to be, right? So the reflection ray needs to have exactly the same angle with respect to the normal than your ray with respect to the normal. So yeah, it just happened to be like that on my render. Okay, so this is color bleeding, right? So basically you have the light of the sun is hitting this object that is kind of like red, and this object right here, which is marble, right, is basically getting that color. So this is called color bleeding, okay? And it's extremely difficult. Yeah, orange or red or whatever. So the technique the technique that is used to mimic this this effect is not called ray tracing. It's called radiosity. Okay, and it's a totally different algorithm. Okay, but yeah. Okay, can I continue? I think any other question? Are all the questions sufficiently answered? I guess. Yes. Okay. So again, we need, if this guy is reflective, we need to get the color of the purple one, right? And because we need the color of the purple one, we need light information, but we also need to see if this guy is under shadow, right? So before I said that the way we compute if something is under shadow is that is by throwing a ray in direction of the light and basically tracking if there is any geometry between me and the light. And if there is geometry, if I hit something, it means that I'm blocked. But look at this example. What do you think you need to do? Do you think it's doing the same, like literally throw an array, right, and see if anything is blocking? What do you think? Think about performance. Imagine that there are other objects here. Imagine that there's another sphere here. Is there any better way to decide if this point right here is under shadow? Probably clip it. Yes, kind of, exactly. The thing is, in this case, the vector, right, is basically on the opposite side of your normal, right? So when you're checking if something is under shadow, before sending this secondary ray to see if there's geometry basically between you and the light source, the first thing that you need to check if it's your normal is on the opposite side of the light light vector, right? Because if you itself is if your surface your own surface is basically like facing away from the light, it means that you're obviously you are blocking the light, right? So yeah, that is, it's just to make it to have like a better performance, right? Otherwise, imagine that there are 1,000 spheres in this thing, right? It will be very costly, right? That you need to check if there's something in between, blah blah blah. Yeah, you don't need to do that. Before literally sending the secondary ray, you always need to check if your normal is on the same side of the light, right? So if it's on different side, it means that you're under shadow with this light in particular, right? Because you can have another light on the scene, right? Scenes can have different amount of lights, or not only one, right? You can have a different amount, like 3, 4, whatever. So first step of your algorithm, you first check your normal with the light with the light vector. If they are basically on opposite side, it means that you are under shadow, right? So you don't need to compute the rest. In this case in particular, right, I hit here, right, and I check the light vector with my normal vector. They are both on the same side. It means that I am not blocking the light, so then I can shoot the ray, right? So that is what I have in the next slide, like this, right? So remember, you will basically repeat the same for every pixel, right? So you're shooting rays for the pixels, blah, 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 and eventually you get to this pixel. So now you throw a ray on this direction, it hits the floor, right? And same process, right? You will have this as light vector, right? You check your light vector with your normal. If they are on the same side, it means that you are not blocking the light. Then you need to throw the ray and see if something is between you and the light. In this case, it is. S1 is basically blocking you, and because you get into this intersection, right? This is the way we compute ray trace shadows, right? Good. Any other question regarding this topic? Good. So let's continue. Okay, so now we were talking about intersections with spheres, and we already have those equations and we know how to compute those intersections. But now I'm showing you a intersection, but now with a plane, right? So we haven't discussed how to get intersections with planes, right? So let's talk about ray plane intersections. So let's imagine that we have something like this. We have the camera, we have a ray. We need to compute this intersection here, and we have a plane, right? So one of the easiest way to represent a plane or to define a plane in computer graphics is by defining a normal and a point that is on that plane, right? That is, oh, sorry. Someone is asking, could you repeat the process? Can you tell me which process? You mean the process of getting the ray tracing shadows? Which process do you mean? Okay, good. Okay, so again, this slide is basically representing the process of knowing if you're under shadow, right? It's basically this ray tracing shadows. So I first throw the ray. I hit the ray with, in this case, this plane, right? And I have the normal of the plane, which is this one. And I have obviously the position of the light, so I can compute the light vector. I mean, I didn't draw the light vector here, but imagine that there's like a, right? There's a yellow arrow here, right? So the first step is you need to get the dot product between your normal and the light vector to see if those vectors are basically on the same side, right? So if the dot product is positive, it means that they are on the same side. If it's negative, it means that they are on different side. So if it's, in this case, it is on the same side, which means that this surface, the surface of your intersection, is not blocking the light, right? So then you throw a ray on the direction of the light, searching for other objects on your scene, and if you hit something, in this case you hit S1, it means that there's something between you and the light, and obviously you're occluded, right? So now you can definitely say, okay, I'm under shadow, right? What I was saying on previous slides is that in this case in particular, when you get into this intersection, right, because the light vector and the normal vector, right, they're on opposite side. If you take the dot product will be negative. You don't need to throw a ray on this direction because you are blocking the light, right? So there's no need to throw anything else, right? So it's obviously cheaper. And remember, when you are in shadow, what we usually do is that remember we have three components: ambient component, diffuse component, and specular component. So if anything is under shadow, we usually, what we do is just drop the diffuse and the specular. We drop them to 0. So we only get the ambient component, okay? Is that answering your question? Okay, good. Okay, so ray plane intersections. So let's see. I was saying that one way to represent a plane, which is very convenient, is that you have basically a vector that is representing the normal of the plane and a point on that plane, right? So once you have that, and you have a camera, basically the position of the origin of the ray, and you have the ray direction, imagine that you have, or you could compute these two distances, basically orthogonal, right? Orthogonal to the plane. You could have this distance right here and this distance right here. So basically, these are creating two similar triangles. You agree? These triangles are similar, right? There's this is actually a right angle, right? So this is orthogonal. So these are basically similar, which means that if I get if I divide this distance B, between distance A, I get like the scaling factor from which I could multiply A to become B. You agree? Right? And because these triangles are similar, these are similar triangles, I could get that same number, the same scaling factor between A and B, and I could multiply R by times that factor. Okay? So let's see the equations. So how can we get this distance B? So if we have the normal of the surface, and what we need is the distance of this distance that is basically on the same orthogonal direction with respect to the plane, this is just the projection of R into the vector, into the normal vector, right? You agree? So basically, B is the dot product between R and the normal, right? Because it's just the projection, right? It's the distance, right? Then the way you compute A will be basically the projection of another vector that we need to construct. That is a vector that goes from the camera position or from the origin of the ray to the point in your plane, right? So imagine that we take that vector is called W, or we can call it whatever. And the projection of that vector W on the normal will get you this, right? This distance right here. So you compute A by taking the dot product between W and the normal. And W is basically P minus C, right? So now you have these two distances. You get A over B, right? The big distance over this distance. And you basically get a number K, which is basically a scaling factor, right? And okay, somebody said, yes, that will be negative though. Yeah, but it's not a problem, right? If it's negative, imagine that it's minus 100 over minus 30. It doesn't matter. The ratio will be the same, right? So it doesn't matter. What you need is basically the ratio, right? So you need a scaling factor. So now this intersection will be the vector R times that scaling factor, right? Plus the position of C. And someone is asking, P is any position on the plane? Yes, P is any position on the plane, right? So obviously you need those things, right? So if you want to compute the intersection between a ray and a plane, you need a proper definition of that plane, which means you need at least a vector and a point on the plane, but it can be whatever. Yeah. I mean, in this diagram in particular, I put P on the same position of N, but it could be anywhere, right? Because in the end, it's just a projection. So P could be here, right? And W could be this vector, but it's the same. The dot product of this very large vector into the normal, right? The dot product with the normal will be exactly the same distance, right? Because it's just a projection. Good. Questions of this ray plane intersection? Okay, good. So Nam has a question. Yes.
Hey, I am confused about how you established B is equal to the dot product between R and N. Can you explain that one more time?
B. Well, R is your the direction of your ray, right?
Right.
So by taking the dot product between R and N is this direction, right? So basically, I mean,
Right.
B and A are these distances, but they have exactly the same direction as N. So if you take the dot product between R and N, what you're doing is you're just projecting R into the N vector. So you will get this distance.
I see.
Remember, you need to remember that the dot product is just projection one vector to the other, right? So when we want to compute, for example, the angle between two vectors, right? That is when we actually need we need to have the two vectors need to be normalized, right? In those cases, they need to be normalized, right? But in this,
right, yeah, they're all unit vectors, right?
yes, exactly.
Yeah, it makes sense then.
But even if it's not, if they're not, for example, W is not a unit vector, right? So normally the normal it is a unit vector, but W is not, right? So W is not normalized, right? Because what you want is its projection, its orthogonal projection, right? So because W is not normalized, when you take the dot product, you get this distance, right? So this is one of the cases in which we don't want to normalize those vectors. So that is actually a common mistake, by the way. I mean, thanks for asking, because yes, I remember right now that is also something that happened with my students many times before, that when they're doing their math, they somehow assume that, oh yeah, all the vectors they need to be normalized all the time. So for example, if you normalize W, yeah, it will not work, right? Because now W will be very tiny, so now the distance will be very tiny, and basically the ratio will be nonsense, right? So this is one of the cases in which we don't need to normalize the vectors, right? So W is just the vector as it is.
Just quickly, so when you said projection, you really mean the magnitude after projection, because B is a scalar, not a vector.
The magnitude after, yes. Yeah, but what do you get from a dot product? You get a magnitude, right? You get a number. You don't get a vector, right? Cross product gives you a vector, but dot product gives you a number, right? So the number you get from getting a dot product between two vectors is a magnitude, that is basically the distance of the projected version from one vector projected onto the other vector. I think I explained that already on a previous slides, when I was even like showing you like the dot product concept, and showing you that the dot product is just literally a projection, right? Projecting one vectors on other vectors. Okay, so yeah, we're almost done. So yeah, I also need to. I have also right triangle intersection. So let me just quickly say that I have more slides, but I have, yeah, don't worry, we can cover that on Monday. So just very quickly, that was ray plane intersection. So now let's think about right triangle intersection. So the way we do this is we basically first compute the intersection to the plane from that triangle, because remember, a triangle is always on a plane, right? Or it can always representing a plane, and you can get any point from that triangle as a point on the plane, and you can get the normal of the triangle, and basically you have all the information, enough information to compute the intersection between that ray with the plane, right? And then you get this. And then what you need to compute is, okay, I have the intersection between the ray and the plane in which this triangle is basically living, right? Now I need to know if that intersection is basically inside the triangle or not, right? So we compute the barycentric coordinates, and if you remember, if the barycentric coordinates are more than one, it means that the intersection is outside the triangle. If it's exactly one, it means that it's inside the triangle. But yeah, we can still talking about this on Monday. So thank you so much again. Please go check If you haven't signed up for your face-to-face, or if you miss one of the face-to-face, please go and solve that problem immediately. And please, what else? Yeah, the survey, obviously. Yes, if you haven't solved the survey, please go and check the survey. And we also release the ray tracing assignment. So it is important for you to read that document. So I will talk about that on Monday. I will give you a couple of hints, and I will kind of explain a little bit. But please check the document already, because the ray tracing assignment is challenging, and you basically have 1 month. Okay. Thank you so much. Bye. Yeah, and I know people is saying, oh, but I'm starting the shading one. Yeah, but they're basically related. You will see that they're basically related. Thank you, everybody.